So let me begin. Today, for the next few lectures, we're going to be talking about Hopfield networks as auto-associators and related models. Where is everybody, right? Where are my TAs? Can one of you guys monitor Piazza just in case somebody's, has questions? Thank you. It's all right.
Someone asked if live stream is broken.
Pardon me?
Someone asked like 30 seconds ago if the live stream is broken.
So the live stream, can you guys check if the live stream is on?
Should be. It was before. I'll turn it on.
Okay, it's up. All right. It's up. Thank you. So, all right, guys. So, the story so far, we've looked at neural networks primarily for computation. The kinds of networks we've looked at are strictly feed-forward structures. Something comes in, it gets processed, that outcome gets processed, that outcome gets processed. So for any given input, once that input has been processed by a neuron, that neuron is never going to see the outcome of that processing again from any further downstream from any further downstream computation. This is the kind of processing these are the kinds of networks we've seen so far. The one to the top right. But now, today, we're going to start considering networks of this kind. This is not a recurrent network. This is a network where the output of a computation goes back into the network. So in this kind of situation, what happens? This is the question we're going to be looking at. Right? Do you see the distinction between feed-forward structures and these guys? These are loopy networks, where when something is processed, that outcome can go back and affect the neurons again and change the neurons' outcomes. So here is a more explicit model, right? We're going to consider the simplest model for now, where every neuron is looking at a weighted, the affine combination of the outputs of other neurons. We'll consider threshold activations. So if this affine combination exceeds a threshold, the neuron's going to fire, otherwise it doesn't fire. And what happens here is that the output of one neuron affects the inputs to other neurons. And the outputs of those neurons in turn affect the input to the first neuron itself. Let's look at the simplest variant. Once each neuron talks to every other neuron and every neuron talks back to the first neuron, you have the ability to actually make these weights symmetric. And so this is the kind of model that we're going to be looking at, where the weight of the connection between a neuron I and a neuron J is exactly the same as the weight of the connection from neuron J to neuron I. Again, each neuron is looking at an affine combination of the outputs of the other neurons, and the activation is a threshold activation. We're going to be considering a very specific form of outcome without any loss of generality, namely that the neurons have a +1, -1 output. We are looking at binary neurons with output is plus or minus 1. Now, this kind of a network is what is called a Hopfield network. This is distinct from the other structures we've seen so far. Other structures we've seen so far, every one of them was a feed-forward network. This is a loopy network, where once a neuron processes an input and outputs something, what it outputs can go back and affect the neuron and make it output something else for the same input, right? So here is question? No. So here's how the neuron actually operates. Each neuron is looking at an affine combination of the outputs of other neurons. If this affine combination exceeds a threshold, it's going to fire, otherwise it doesn't fire, right? So now consider what happens. Let's say the current output of the neuron is +1, and the affine combination of inputs is positive. Then what happens? The affine combination of inputs says that the output of the neuron must be +1. The neuron is currently also +1, so the neuron is not going to change its sign. On the other hand, if the neuron is currently -1 and the affine combination is positive, the neuron must now become positive. It's going to change its sign, right? Similarly, if the affine combination is negative, the neuron only changes its sign if it's currently positive. If it's already currently negative, it's not going to change its sign. So you can think of the whole operation like this. At each time, at each computation, each neuron receives a field, some kind of a field, which is the affine combination of the outputs of all other neurons. If the sign of this field matches the sign of the output of the neuron is going to stay as it is, otherwise it's going to flip. Everybody clear with this, right? So here is how we can actually write it in arithmetic, which is that if the sign of the output of the neuron of the affine combination matches the sign of the neuron, then the neuron doesn't flip, which means if I take the product of the current output of the neuron and the affine combination that comes into the neuron, this product must be positive for the neuron to not change its sign. Because if this product is positive, it means the neuron is either one of two conditions has happened. This affine combination is positive and the neuron is positive, or the affine combination is negative and the neuron is negative. If the two are mismatched in sign, then the neuron is going to flip. So the way we can say it is that if y times the weighted sum of the outputs of the other neurons plus the bias is positive, the neuron retains its current output. Otherwise, it flips its sign. Y becomes minus y. So, yeah.
Does different sign guarantees a flip?
Yeah.
The affine combination can be smaller.
We are only looking at the sign, right? So if the affine combination is negative and the current output is positive, then the current output is going to become negative. It's going to change. And vice versa, right? If both of them have the same sign, it will not flip. Yeah.
How is the weights updated?
Pardon me? How is the?
Weights.
I didn't get the question.
The W's?
So,
Get updated at all?
so we're just speaking of the operation of the neuron. There is no update over here. Right? This is just this is when I'm speaking of how the network performs computation. This is what it happens. So this basically, to summarize, a neuron flips if the weighted sum of other neurons' outputs is of the opposite sign from its own sign. But what happens in this case? So let's say I have a pattern, and the weighted sum of the outputs of the other neurons is a different sign from the output of the current neuron, so the neuron flips. When the neuron flips, because this neuron has flipped, it changes the field at other neurons. This may cause some other neuron to flip. When that neuron flips, that changes the input that this neuron has received. And now this may cause this neuron to go back and flip all over again, right? So the behavior is no longer just a one-step process. It's going to keep looping. So here, for example, here is a initial setup of our network. I have red and blue edges. Red edges have value -1. Blue edges have value +1. They're all binary. The neurons, again, as we saw, are either +1 or -1. Now look at what happens to this guy here. This neuron here, the total input is positive. The current value of the input is negative. Output of the neuron is negative. So because the field is positive and the neuron is currently negative, the neuron's going to flip. But the moment this neuron flipped, if you look up at the neuron at the very top, the field at that neuron, which has 3 inputs coming in, or 5 inputs coming in, and the current sign of the neuron are mismatched, so that's going to flip. And because that has flipped, that's going to cause this first neuron to go back and flip all over again, right? So you can see that these things, the behavior can actually get loopy. So here is what is going to happen. If the sign of the field at any neuron opposes its own sign, it flips to match the field, which will change the field at other nodes, which may flip, which may change the field at the current neuron, which may flip, and so on. And so the overall behavior that you see is going to end up looking something like this, right? All the neurons which do not align with the local field will flip, and they're going to go on flipping. Now this I've just shown 20 cycles. I have a neuron network of 20 neurons, and I've just sort of shown 20 evolutions, but this is actually a real simulation, and here's what happens. So all the neurons are going to keep flipping, right? And after 120 here, I've only run through this for 120 evolutions, but you see what is happening over here, right? So everybody clear what's happening, right? Yes?
I just want to clarify. So in a single pass through, so do the neurons only flip once, or can they flip multiple times?
What do you think is happening here?
So multiple times. Okay.
It's good because the neuron flips. It's loopy, right? The neuron flips. It caused some other neuron to flip. That changed the field. So the neuron is always trying to output something that matches its input.
Right, but will they like converge to a stable state, or?
That is the magic that we're going to answer, right? So here is my question. Will this behavior continue forever? That is a question, correct? Okay. Let's try to answer this question. To answer this question, anybody? Questions? No. Yeah. Yeah.
I think if you update the W's,
We're not speaking of updating the W's at all, right?
then I feel like it might not converge.
Aha. Hang on. Hang on to your socks, right? So here's what happens. Consider a single neuron, right? So the neuron receives an input and it has an output, right? So let y minus be the output of the neuron just before it responds to the input, and y plus be the output of the neuron just after it responds to the input. Okay? So if the sign of the field matches yi, then yi is not going to flip. So y plus is going to be the same as y minus. You agree? Right? So in this case, if I take the product of y and the sign and the field after it's responded and subtract from it the same product before it's responded, this difference is going to be 0 because y plus and y minus are exactly the same. Right? Now let's consider the other case. Let's say the sign is not equal to the sign of the field is not equal to the current sign of the neuron. What happens then? Then the neuron's going to flip, right? So now this term, y plus times the sign, once it has flipped, y plus times the sign is a positive number because the neuron has flipped to align itself with the field. This guy is a negative number. The difference between the two, because y has flipped, y minus is minus of y plus, right? So I can write this as, group this as the field times y plus minus y minus, which is 2y, whatever y was, right? And so this is going to become 2 times y plus times the field. You agree? And this number is positive, guaranteed. So anytime a neuron flips, it's going to increase this product term, which is the product of the output of the neuron and the field at the neuron. Right? Questions? And globally, let's take this product and sum it over all the neurons. Right? I'm going to define this term D, which is a function of all of the neurons in the network, which is simply the sum over all of the neurons of the product of the output of the neuron and the field at the neuron. This, if I write it in, basically it's the sum over all neurons of these of the product of the field and the neuron, right? This is this term in the middle in the blue is this sum over all neurons. I'm going to assume that there are no self connections. A neuron doesn't feed to itself. Now, let's say any neuron has flipped. For any neuron that has flipped, this results in a change in D, in this D term. And this delta D is going to be the value of the D after the neuron has flipped minus the value of the D before the neuron has flipped. What do you think this term is going to be? Is this going to be positive or is this going to be negative?
Positive.
It's going to be positive, guaranteed positive, right? How much will it change by? What is the largest amount that it will change by? Assuming the weights are finite, there is an upper bound on how much it will change by. Let's look at what these values are, right? So delta D is simply going to be yk plus minus yk minus times the field at the neuron where you're assuming that only one neuron has flipped, right? Assuming all the other terms. So this term is always positive. Every flip of a unit results in an increase in D. So here's what we get. First, now if you look at D, D is this guy over here, right? Which is the sum over all the neurons of the product of the output of the neuron and its field. It's bounded. It's bounded because all the y's are either +1 or -1. So this term, this first term, is simply bounded by the sum of the magnitudes of all of the weights. The second term is bounded by the sum of the biases. So the minimum increment in D is going to be 2 times this guy over here, right? In any case, so anytime a neuron flips, what is the smallest change in D? The smallest change in D is this product term. This is the field at any neuron. If you take, because you're multiplying the field by the output of the neuron itself, which is either +1 or -1, the change in D at any neuron, if it flips, is going to be 2 times the field at the neuron, the magnitude of the field at the neuron, right? And the smallest such change is going to be the smallest increment in D if any particular neuron flips. Is that clear? You look puzzled, right? Did I get you? Puzzled or clear? Clear, right? So here it is. There's a smallest limit to how much D can change in one step. There's an upper bound on the value of D. So how many times can this network change? There's an upper bound, right? D divided by the smallest delta D is the maximum number of changes, flips that you can get to answer your question. It's not going to go on forever, right? So basically what we've shown is that this network is going to behave in a loopy fashion. It's going to keep evolving, but it doesn't evolve forever. When does it stop? To answer when it stops, we're going to look at this guy here. Remember, I just took the sum of the product of the fields of the neurons and the output. I'm going to flip the sign. This is minus of the D that we just defined. I'll call this the energy of the network. And if I call this the energy of the network, the evolution of a Hopfield net is constantly decreasing the energy of the network. It's going to stop when the energy of the network can no longer change, right? So here's the story so far. Quick summary. A Hopfield network is a loopy binary network with symmetric connections. Every neuron in the network attempts to align itself with the sign of the weighted combination of the outputs of the other neurons. So if you start off with an initial configuration, which is the input to the network, so to speak, then the neurons in the net will begin to flip to align themselves with their local fields. And this causes the fields at other neurons to change, making them flip and so on. Each evolution of the network is guaranteed to decrease the energy of the networks. And the energy is, of course, upper bounded, and the decrements are lower bounded. So the network is guaranteed to converge to a stable state in a finite number of such steps. Questions? Anyone? No? Okay. So I just defined this term energy. Where did this term energy come from? Which hat did I pull this particular term out of? Let's take a look. Goes back to something called spin glasses. So when Hopfield was writing about Hopfield networks, there was a beautiful book by Giorgio Parisi, he's a physicist, on the spin glass effect. And the spin glasses are about the evolution of dielectric media, specifically glass. Glass, as we know, is an amorphous solid, and the glass is a specific state of matter. I'm not speaking of the silica variety. The general idea here is that when in a disordered magnetic material of this kind, every element in the magnetic material is a magnetic dipole, and all of the magnetic dipoles in the material are going to cause a field throughout this medium. And every local dipole is going to try to align itself with the local field. Now, dipoles are obviously either north-south or south-north, right? But when the dipole flips, it's going to change the field elsewhere, which may cause the other dipoles to flip, which may change the field of the current dipole, and so on. So you can define the total field at the current dipole as a sum of two terms. Now, this is physics. You've done all of this in college, which is, the energy in the total, you can think of the potential energy in the total medium as the sum of the contributions of the individual elements, and each individual element's own energy is simply the product of its own value and the local field. So this is going to the total field at the current dipole is going to be the weighted combination of all of the other dipoles, where J, the uppercase J, Ji, tells you how much a dipole at some location affects the current dipole. It depends on the medium and a bunch of other effects. And then you may have an external magnetic field, which is Bi. So P is the vector. Now when I say F of P, P is the vector position of the ith Pi. Pi is the vector position of the ith dipole. So the field at any dipole is the sum of the field contributions of all the other dipoles. Now, the contribution of a dipole to the field at any point depends on this interaction J, which is derived from the Ising model for magnetic materials. It's a beautiful paper, 1924. Now, a dipole flips if it is misaligned with the field at its location. So you have this field, F of Pi, and if the dipole is aligned with that field, it's not going to do anything. If it's misaligned, it's going to flip, right? Sound familiar? Xi stays Xi if the sign of the field is this, times its own value is 1, otherwise it's going to flip. So dipoles will keep flipping. A flipped dipole changes the field at other dipoles, some of which will flip, which will change the field of the current dipole, which may flip, etc. This can go on. When will it stop, right? So to determine when it will stop, now we can actually look at something called the Hamiltonian, or the total energy of the system. Again, these are all physics concepts from physics, right? And the total energy of the system is going to be minus half times this term, which is simply the product of each dipole and its local field. The product of the dipole and the local field is the potential energy contribution of that dipole to the overall system, which, if I just expand it out, is this term to the right, right? Now, this guy is obviously a function of the arrangement of all of the dipoles in the medium, right? If I were to sort of come up with some hypothetical arrangement, hypothetical line where I could place all of the potential arrangements of the dipoles along the line, every organization of the medium has a potential energy, a Hamiltonian. Different configurations will have different energies. And if this function is going to have some kind of a shape. So what happens if you start off the system at some particular position? It's going to begin evolving, and every evolution is guaranteed to decrease the energy of the system. When will it stop? It stops when it hits a local minimum. Now, so these systems, these thermodynamic systems, have a nice property. If they are stable, if they have sort of hit some kind of a locally stable configuration, what happens when you perturb them a little bit? When you perturb them a little bit, they're going to begin evolving and go right back to the stable state, because they're going to go back into the energy valley, right? So the system remembers its stable state and returns to it. Yes?
So I have a question. So I get that if you change one of the neurons, and then the easiest way for it to go back to the stable configuration is for it to change back. But what if you change, say, neuron A, and then you don't start from changing back neuron A, but you change something else, its neighbors? Will that still make it go back to?
It doesn't matter what happens, right? if I change one neuron, it may not be that neuron may not immediately flip, but what you are guaranteed is that any consequent change is going to lower the energy. And that is going to cause further lowering of energy. So no matter which order it happens in, I've drawn this in 2 dimensions, but you can think of this as a ball. Instead of coming straight down, it may wander around, but eventually it's going to end up at the bottom.
Yeah, but I guess my question was, I understand that we'll go back to the stable configuration, but will that go back to the same snapshot of the stable configuration as it started with? Would that be a different stable configuration?
Let's answer that question, right? So if the energy valley is large, you'd expect it to go back to the same stable configuration.
Oh, I see.
Right? It's a valley, right? But now, so let's go back to the Hopfield network. What is this energy over here? This is analogous to the potential energy of a spin glass. The system will evolve until the energy hits a local minimum. So this bias term, by the way, this bias term is the equivalent of having an external magnetic field on the medium. Typically, we won't actually you invoke the bias. It's in terms of the network, it's like having a single extra neuron that's pegged to 1. And changing this bias can change the behavior of the network, but conceptually, having a bias is simply like having an extra neuron whose value is always 1. So I won't actually invoke the bias in significant portions of the rest of this discussion unless it is explicitly required. Okay? So here's how I'm going to write it. Here is the Hopfield network again. There, on the top left, is how each neuron in the network responds to its current field. The output of the neuron is going to be +1 if the field is positive, -1 otherwise. Or alternately, if the neuron is going to flip if the product of the field and itself is negative. The energy is the same as what we had earlier, except I'm writing it without the bias, and now I'm only actually summing for j less than I. It doesn't really change the computation because it's summing ij and ji, it's symmetric. The summation is symmetric. So this is a more how shall I say, parsimonious computation of the energy. But regardless, yes?
So when we sum the j less than I, does that mean that we're summing in a certain, as we're iterating through each neuron, in a certain order?
No, it doesn't matter, right? You can flip the order. If I didn't have j less than I, you're just going to get exactly twice this value. Right? Think of this. If I just say j not equal to I, yes, you're going to get wi j xi xj plus wji xj xi. So I just got rid of the extra 2, which makes it strictly analogous to what we had for the spin glasses. There's a half term, that's all. But the point is the system is going to evolve until this energy hits a local minimum. Now this above equation is a factor of 0.5 off from the earlier definition, just so that we can be conformant with the thermodynamic system that we saw earlier, right? So here's how the system is going to evolve. This guy is going to have some behavior over all possible configurations. You started at some configuration, it's going to evolve till it hits a local minimum and the energy contour. This is what we will call a content-addressable memory. Have you heard this term before? Addressable memory. No? So think of a standard memory system in your computer. How do you address it? You give it an address, right? You say this is the pattern located at ABCDE, at this specific address. This is who's the guy living in 5421 Beacon Street. That's my address, right? So the address is independent of the content. But there's a different way of addressing content. I give you a partial content and you say, tell me all of it. And there's reasons to believe that the human brain doesn't really work with an addressing system. It's based, you invoke ideas based on, you invoke stuff or you recall stuff based on what you're recalling, right? Think of this. You're walking down something, you smell something. It reminds you of your childhood. That's because that this clip is gone. Oh wow. I'm not entirely sure what happened. Where? Ah. Thank you. So the point is, you recall stuff by content, not by some addressing location. Content addressable memory is generally a computational equivalent of this paradigm, where if you start off with a partial pattern, you're able to recollect the entire pattern. And guess what? This guy here is just a content addressable memory. You can think of each minimum as a stored pattern. And now if you present the system with a corrupted version of the stored pattern, the system is going to evolve, and it's going to pull back the stored pattern. So it's called a content addressable memory, also called an associative memory. Now there are lots and lots of content addressable memory architectures that have been proposed over time. Hopfield Network just happened to be one of them, but it's a pretty cool idea as a concept, right? And what is really nice is that it's invoking some fairly simple ideas. So in high dimensions, this is what you're going to have. You're going to have some high dimensional energy contour, which has local minima. Each local minimum is a pattern that is stored in the system. And then if you corrupt the pattern and you provide it with some initial value, which is some corrupted but partially recalled version of the pattern, it can work its way and recall the entire pattern. So the network will evolve until it recalls the pattern. And yes?
So we're talking about when you say it's recalling the pattern, you're talking about the actual states in each neuron.
Yes.
That's the pattern.
That is the pattern.
And when you change it, it's going to move. It's going to change all the neurons until it gets to the pattern that it most remembers.
Exactly. The closest pattern that it remembers, right? So it's such a beautiful concept, right? And even more interesting, that we've shown that every change in the network is guaranteed to decrease the energy in the network. So the path from the initially corrupt value that you give it to the recalled pattern is monotonic. Now, how do you actually think of it? Can you try to visualize the whole thing? Now remember that if I'm speaking of binary patterns, then the patterns all live on the corners of a hypercube. Every value is either plus or minus 1. So you can think of this energy, your actual energy contour is not going to look like this guy. Your energy contour is a function defined on this n-dimensional hypercube. There is a notion of nearness and distance. Something that's 1 bit away, it's a 1 bit change away, is 1 edge away. You can count the number of edges from every point to every point. So this is the point, is that I'm trying to show you that this figure I've shown you here is not entirely hooky. There's a notion of neighborhood that you can actually impose on these patterns, and the evolution is going to be along edges, always walking to the closest edge, which has a lower energy, right? Now, for threshold activations, the energy contour is only defined on the corners of the lattice, but then you can also have tan-H activations, which also go between -1 and +1, in which case it's going to be more of a continuous function. Typically, we speak of discrete binary patterns. But regardless, I can now write the energy of the entire network in matrix form. I can write all of the weights as a weights matrix. The W matrix is now symmetric because all the edges are symmetric. This is not required. We are just working with the symmetric definition, because it doesn't really matter whether you make it symmetric or asymmetric, the concept remains the same. And the energy is simply this little quadratic function, y transpose wy. And now, can somebody tell me, now that I've shown you that it's a quadratic function, how many minima will it have? Thank you, right? Not necessarily one, but it can have a ridge, right? You can have a fold. So it depends on the weights matrix. But yes, it's going to have minima. Now, so consider the simple 2-neuron network with tanh, right? You can see the energy contour as a function of the two outputs of the 2 neurons. I've used a tanh network, A, because I found this figure on the web, but B, because when I actually have a continuous output, you can actually show how the energy changes continuously, and those are equal value contours. There are 2 minima, right? Why are there 2 minima?
Is it because there's 2 neurons?
The energy, yes, but there's more to it than that, actually, no. So think of this. We said it's a quadratic of y, right? Y transpose wy. What happens if I change the sign of y? The energy doesn't change, right? So if any particular pattern y is a minimum energy pattern, minus y is also a minimum energy pattern, because both of them have exactly the same energy, right? Which is why you have 2 minima, one for some stored memory y, and also its inverse, the arithmetic inverse, minus y, right? Now, and the blue arc over here shows what would typically happen. If I start the network off at some arbitrary configuration, it's going to evolve slowly and work its way to the closest stable pattern, right? Same thing. Now, if I have 3 neurons, I can still have the same kind of structure here. You might have things like this, right? You have a stable state, which is this guy, -1, 1, -1, and then if any state is stable, then the diametrically opposite corner has also got to be stable, simply because flipping the signs is going to give you a stable structure, right? Now, yes. So here are some examples I pulled up from the web. This guy, the top left, or the figures to the left are patterns that someone has constructed a Hopfield network to remember. Each pixel is represented as a +1 or a -1. So this original guy has some m cross n, maybe 600 pixels in all. So your Hopfield network is going to have 600 neurons. And the Hopfield network is designed such that this particular pattern is a stable pattern, or something very close to it is a stable pattern. Now, in the middle panel, you have this figure. In the uppercase, the figure has been completely corrupted by noise. In the lower case, half the figure has been erased. And now the network has been let to evolve, and it slowly converges, and the reconstructions you get are shown to the right. In the first case, it pulls back Bugs Bunny. In the second case, Chip and Dale are back, right?
But it's different from the original.
Which one? There's some little bits of specks of noise, but it's the same figure.
Yeah, but the noise part.
Yeah, it's not going to be. It's not perfect, but the point is, someone has designed the network. Obviously, they have not got it exactly right, right? We're going to look at, yes. No, they're 2 different networks. Let's look at that, right? Here is someone put this up, and someone is trying to store these 2 figures. Then he started with this figure, and then he's corrupted it. He lets it evolve. It goes back to this guy, right? And you can see. The same network in this case is storing both patterns. Now here is a penguin, right? 3 patterns actually: penguin, the world, the end, and then he lets it evolve and goes right back, right? So very cool. Question is, how do you actually build this network, right? Yeah.
I wonder if this is using like
What do you mean?
Like you have a key and then you sort of unlock it by giving the key and then.
I haven't thought it quite in those terms, but I'm sure you know. There's more than an analogy over there that's totally valid. I'm just, well, yeah, but we are going to look at, what we are going to look at in the next few minutes, next 40, 30 minutes, is how we can actually build a network to store the patterns we want. And then we have a couple more classes of the same thing, right? So here is the computational algorithm. We initialize the network with some pattern. So you just, all of the y's with some initial pattern. Then you're going to iterate through the network. At each neuron, you're looking at the local field, and you're flipping the sign, or you're setting the sign of that neuron to match the local field. It's very simple. And updates can be done sequentially, or they can be done all at once. You know, just update all of the neurons in one step, do it again. Regardless of how you do it, you're going to converge when this energy doesn't change any further. So to answer your question about why the figure had some speckles, it's also likely that they stopped the evolution before it had actually hit the minimum, right? So the story so far, a Hopfield net is a loopy binary network with symmetric connections where the neurons try to align themselves to the local field caused by other neurons. Given an initial configuration, the pattern of neurons will evolve until the energy of the network achieves a local minimum, and the evolution will be monotonic in the total energy. The dynamics of the Hopfield net mimic a spin glass. The network itself over here is symmetric, so if a pattern y is a stable configuration, so is minus y, you can use the network as a content-addressable memory, which means that if you set these these local minima in energy as saved patterns, as minimum energy, as the patterns you want to store, then if you initialize the network with a somewhat damaged version of this local minimum pattern, it will evolve into that pattern, effectively recalling the correct pattern from a damaged or incomplete version. So questions: how do you actually make the network store a specific pattern? How many patterns can you store in a single network? And how can you retrieve them, right? Better. How much time will it take? So let's look at this first guy. How do I teach the network to remember this specific image? First thing, if the image has n pixels, the network is going to require n neurons, right? It's one element per pixel, obviously. Now, every neuron, the way we designed it, connects to every other neuron. So you're going to have n times n minus 1 over 2 weights in all. Simple, straightforward arithmetic, yes?
If you want to have n neurons, why don't you just have an array of n cells and just save the image there?
Pardon me?
Why don't you save the image in an array? Why go, if you need n neurons for like a neuron for every pixel, why don't you just save that pixel in an array? That's it.
This is content-addressable memory, right? My point is, if I have, I want to be able to get back something from a damaged version of the image. Now, now if it's just storing one pattern, I know in advance exactly what I'm trying to recall, not a big deal, right? This really becomes more interesting when I actually become able to store more than one pattern at a time, right?
So it does have a factor compression, I guess.
Pardon me?
So it does comprise this, like, so it doesn't need as many weights as the number of pixels.
You do, at least the way we've designed it, defined it, right?
What you're saying is that it doesn't, okay, you have this, your picture, for example, if it's perturbed or damaged, it doesn't just flip back in one go, it has to go through.
It evolves.
Kind of spread back out.
It evolves backwards,
Yeah.
right? Yeah.
So you couldn't just have a simple memory store with operations on each cell.
Yeah.
You
And
have to store.
And remember that at least part of this whole thing was designed trying as an attempt to mimic human recall. So Hopfield's original papers, which were, I believe, in Nature, were trying also to model human recall, which is based on partial recall pulling up full recall, right? But then, from a practical perspective, Munira's question is right. If I'm just going to be storing one pattern, why not just store it? I know exactly what I want, right? That's not where the fun is. So first, let's see how we can store one pattern, right? A network that stores a pattern P also stores minus P, naturally, because of symmetry. This we've already seen, right? No big deal. Now, a network can store multiple patterns. How is that? Because this energy contour can have multiple local minima. And every local minimum is going to be a stored pattern. Of course, you're going to have for every local minimum its mirror image, which is also going to be a stored pattern, meaning you can flip on the other side and expect, because P and minus P are both local minima, right? Now let's try to start storing a single pattern. Let's say this is the pattern I want to store, 1, minus 1, minus 1, 1, minus 1, which means that I'm not really sure what the second figure is doing. I'll figure this out later. But let's say I want to store a pattern, right? I want to design, what does this mean to store a pattern? I want to design my weights such that that specific pattern is a local minimum in the energy contour, right? So consider storing just one pattern. What is the criterion we want? How do you know that a pattern is a local minimum? Or how do you know that a pattern is stored? A pattern is stored if, when the system is initialized in that pattern, it doesn't change, right? That means at every neuron, the sign of the field must match the field, must match the output of the neuron. This is not sufficient. This only means that the pattern is stored. It doesn't necessarily mean the pattern is recalled. These are two different criteria. So what I mean is that if I set the neural network at that pattern, it will no longer change. So the pattern is stable. But if I flip one bit, will it go back to that pattern? Only if it does that is that pattern actually being recalled. So recall and storage are different, stability are two different things, right? Make sense to you? Okay. So the first criterion, of course, is that you want the pattern to be stationary. The sign of the field at every neuron must be the value of the neuron itself. This is how you guarantee that if you set if the pattern is in that configuration, it's not going to change. Every single neuron is happy with its current state. For doing this, turns out you can do this if I'm trying to store just one pattern. I can do this with Hebbian learning. And the Hebbian learning is I start off with a pattern I want to store, and I just set the weight to be the product of the neurons on either side. If both neurons agree, I'm going to set the weight to 1. If both of them disagree, I'm going to set the weight to minus 1. And so let's see if this actually works, right? Now look at this guy. I want the sign of the field at any neuron, which is the sum over all other neurons of the weight times the other neuron. But the way we've defined the weight using Hebbian learning, Wji is simply yj yi. This is yj squared. Yj squared is always plus 1, right? So this just simply comes out as summation of yj squared times yi comes out. Sine of yi is the same as yi, right? It's because this other term, this squared term is positive. It doesn't really affect the sign. So we show that when you actually simply use the Hebbian rule, the pattern is definitely stationary. Is this stable? Stationary and stable are different things, right? Now, so we've shown the pattern is stationary. Is it stable? Now let's go back and look at the energy, right? The energy over here is simply the summation. This is how we define the energy, right? Summation over all the neurons of the product of the value of the neuron and the field of the neuron. But Wji was simply yj yi. So this term is going to be summation Wj squared Wi squared, which is 1. This whole term simply becomes minus 0.5 n times n minus 1. And this is provably the lowest the energy can get for this network where the weights are all either plus 1 or minus 1. You cannot really go below that, which means that the one pattern that you've stored is not only stationary, it's very stable. If you flip a bit or two, it's going to go right back into that pattern. It's the minimum of that quadratic ball, right? So the pattern is stable. So let's try plotting this. Here I'm actually using I'm representing 4-bit patterns. I'm representing the 4 bits using a Carnot map. You recall the Carnot map? Every column is 1 bit flipped with respect to the adjacent column. Every row is 1 bit flipped. So the two outermost edges meet. The bottom and top edges also meet. And I would like to store this one pattern, which is highlighted in yellow. And I use Hebbian Learning to store the pattern. And the figure to the right shows the energy for every configuration. Yellow is lowest, blue is highest. And you can see that when yellow is stored, this is the lowest energy configuration. The negation of the pattern also has a low energy configuration. You can also see that it's stable. If I'm over here, if I start the network over here, it's going to evolve to a lighter shade of blue. From the lighter shade of blue, it's going to go to yellow. You have no guarantee over which of the two it's going to flip to. Right? There's a certain degree of stochasticity on how you actually program it, the order in which things evolve. But you're going to end up with one of the two patterns. Right? Now, so we can store one pattern, and you can store it well. How about storing more than one pattern? I can still use Hebbian Learning. I can use Hebbian Learning, except now I'm going to be averaging this product over all of the patterns that I would like to store. And if I do that, then P over here represents a pattern. So I have several patterns I'm trying to store. I can compute the weights matrix for each of the patterns, the optimal weights matrix for each of the patterns. But when I have several of these to store, I'm going to average all of these weights matrices together, or sum them. It doesn't really make a difference. So when I do this, how many patterns can I store in this manner? And here's where a little bit of arithmetic. For a network of n neurons, the arithmetic says you can store up to 0.15 times n patterns, provided they are far enough. By far, what do I mean? When I have bit patterns, I can actually have a notion of a distance between bit patterns. And where did this number 0.15 come from? That too is a question, right? So let's see exactly where this pattern comes from. Let's say I want to store k n-bit patterns, where each pattern is basically a sequence of n bits. Now, the Hebbian Learning says I'm just going to average over all of the patterns the product of the 2 bits for each pattern, right? So Wij is the average over all patterns of the ith product of the ith bit and the jth bit, as we just saw. Now, for any pattern to be stable, you want the product of the field at the pattern and the desired bit for that pattern to be greater than or equal to 0, right? So you want this field times this y to be greater than 0 for this to be stable. In other words, you want this guy. Now, what is Wij? Wij is simply the sum over all of the patterns of the product of the bits. So I just expanded this out. You want this term to be positive, right? Straightforward. The arithmetic is not very complex. It's very simple. That's a fun part of it, right? Now, here's what I do. Remember, I summed over all of the patterns that I wanted to store. When I computed the weights, I applied the Hebbian Learning to every pattern that I wanted to store. And then the final weights matrix I got was a sum or an average over all of them, right? Now, for each pattern, if I only used the weights matrix computed from that pattern, you know that it's stable. But what is really causing noise is the contribution of the other patterns to that particular weights matrix, right? So just to remind you, here's what we had. If I wanted to store a pattern, let's say I had this. If I wanted to store one particular pattern, +1, -1, +1, let me add a fourth one, just so, +1. Then for this pattern, this weight was going to be 1, right? At the same time, if I wanted to store another pattern, which was, say, like so, which was +1, -1. For this pattern, this weight was -1, right? And the way we did it was we summed the two. This guy is noise. This guy is the good guy, right? For as far as this pattern is concerned, this +1 is the good guy, this -1 is noise, right? So what I've done over here for any pattern is to separate out the contribution to the weights matrix of itself and the remaining patterns that didn't actually agree with it, right? Or that didn't necessarily agree with it. So the first term is where I pulled out the weights contribution from the target pattern, and the second term is the noise that could be enforced by that could be introduced by the other patterns I'm trying to store. You see the separation over here? Now you are guaranteed that for the first term, because I'm dividing by n, that entire term is going to be 1. We showed that the energy is simply going to be n, if you have n neurons, when I use Hebbian learning to store one pattern, right? And if I divide by n, that value is simply going to be 1. So you have two terms over here. The first term is 1. The second term is the noise term. And when will a pattern become unstable? The pattern will become unstable if that entire product is negative, right? In other words, the pattern will become unstable if the second term causes the entire term to become negative, although the first term is +1. So sending that first term over to the right-hand side, the pattern is stable if this noise is greater than -1. If it's unstable if this noise term is less than -1, right? And you don't actually need to memorize what those values are. The arithmetic, again, as I said, is very simple. If you looked at the slides, you could pull them up. But then what we want to do is just this. We want to use this characteristic to decide how many patterns you can store. So let me look at this noise term. For any random set of k patterns, we want the probability that the noise is less than -1 to be very low. If the probability that the noise is less than -1 is high, it means that at least some of the patterns are not really going to be stored. They're going to get corrupted, right? Because the energy over there is not positive, right? Or the energy over there is not a local minimum. The negative energy is not positive. So it turns out that for large n, for very large bits, number of bits, you can actually compute this probability quite easily because you're summing a lot of terms. And when you sum a lot of terms, and a lot of Bernoulli values, this is central limit theorem. It's going to be a Gaussian, right? So this probability distribution ends up having a mean of 0, a variance of k over n, where k is the number of patterns you're trying to store, n is the number of bits. And so for large n, this whole thing is like a Gaussian. And you can show that probability is less than 0.004 if k over n is less than 0.14. So what this means is that if the number of patterns you're trying to store is less than 0.14 times the number of bits in the pattern, then the probability that any particular pattern is going to be unstable is less than 4 in 1,000. 4 in 1,000 is really a crappy number. This is just something Hopfield chose quite randomly. If I want memory things to be remembered well, I want a number that's much, much smaller, right? But then again, remember that this number has been arrived at making some assumptions, namely that n is large, that you're storing a large number of patterns, right? A large number of bits. But let's see how exactly this works out. A network of n neurons trained using Hebbian learning can store up to 0.14 n patterns with low probability of error, where the probability of error is less than 0.004. And this whole thing has been computed assuming that the probability that any particular bit is 1 is 0.5. What do I mean by saying that the probability of any bit being 1 is 0.5? That means on average, half the bits are +1 and half the bits are -1, right? So we also assume that the patterns are maximally distant from one another. What do you mean by maximally distant from one another? You want them to be as far away as possible. Now from our perspective, remember when I drew the hypercube, where is the chalk? Is there a chalk here? So when I drew when I showed you things on the hypercube, right? Is that a cube? So this pattern was exactly the same as this pattern, right? Diagonally opposite patterns are the same. So what is the farthest you can actually get from any given pattern? The number of edges from here to here is going to be n. So the farthest you can get is n over 2, right? So two patterns are going to will be said are orthogonal if the distance between the two is going to be n over 2. We can show that for such patterns. If you look at the inner product between the two patterns, the inner product is going to be 0, right? But then under these conditions, you expect to be able to store 0.14 n patterns. Let's see if this really happens. Again, this is a topological representation using a Karnaugh map. If I'm restoring 4-bit patterns, look at what the energy well is like. If I'm trying to store one pattern, it's easy enough. Hebbian Learning gives me a perfect, beautiful well over there. I'm storing the pattern in its mirror inverse. But let me try to store two patterns. Again, going back, two patterns that differ in n over 2 bits are said to be orthogonal. Because, again, in terms of the hypercube, they're halfway between a pattern, one pattern and its mirror image, right? And if you're using the +1 -1 notation, you can show that the inner product between the two is 0. Now, for more generally, if the number of bits can be written as 2 raised to n m times l, where l is an odd number, then you can show that there are at most 2 raised to m orthogonal binary patterns. Basically, how many corners are halfway between this guy and this one, right? You can show that that number is just 2 raised to m. Now, others may be almost orthogonal, but they won't be exactly orthogonal. They'll be a bit or so off. Now, let me try storing 2 orthogonal 4-bit patterns. I can get up to 2 orthogonal 4-bit patterns. When I do that, you see first that using Hebbian Learning, the 2 patterns are local minima. The 2 patterns are stationary, which means that if you set the network in these patterns, if the network is not going to evolve, their mirror images are also, their negations are also stationary. But then they're not really stable in the sense that if I start the network at any other location, there's no guarantee as to which of these two it's actually going to recall. So you have most of the network is perfectly on the ridge. So the energy contour looks something like this, where all the energy configurations are on this ridge or on a ridge, which are equidistant from both the patterns that you're trying to store, right? But if I make the patterns non-orthogonal, in fact, I reduce the distance between the 2 patterns, something interesting happens. Both patterns become perfectly memorable, right? And because you can see that if I'm over here, I'm definitely going to go to this guy. If I'm over here, I'm definitely going to go to this guy. There are some regions in between where the network can get confused. Now, the thing to note is that 2 is greater than 0.14 times 4. So we're actually able to store more than 0.14 n patterns, right? Let me try to store 3 orthogonal 4-bit patterns. Again, we'll see that all three of them are local minima in the sense that they're stationary. But if you try to flip a bit, you have no saying exactly which of those where you're going to go. But if I make the 3 non-orthogonal patterns, then you get something interesting. Some patterns are very distinctly recalled. Other patterns end up being unable to recall other patterns. So here, for example, the 2 corner patterns, if you set them off at the 2 corner patterns by flipping just 1 bit, I can go off to the top left corner. And the top left corner is a pattern that I do want to recall. But of the 3 patterns I'm trying to recall, only 1 is actually being recalled. The other 2 are not really stable. And if I try to have 4 orthogonal patterns, basically I don't get any, there's no energy contour, it's flat. And if I have 4 non-orthogonal patterns, I do get 1 stable pattern, and you get a lot of other gunk. This gunk happens when the ghost of one pattern, what I mean by the ghost is the negation, collides with some other pattern that I'm trying to store, right? So going back, How many patterns can I store? For a network of n neurons, the arithmetic said I should be able to store 0.14n patterns. But this is for large n, right? N equals 4 is not really a very large n. So let's try to increase the n. Let's try to go up to, say, 6 or maybe even 8 to get an idea of what is really happening over here. For 6 patterns, again, for 6 bits, again, if I'm trying to just store just one pattern, it's perfectly stationary. It doesn't matter where you start, which configuration you start at. There's a energy lowering path which eventually is going to arrive at this one pattern that you've tried to store. If I try to store 2 patterns, now this is a 6-bit Carnot map. A 6-bit Carnot map is kind of odd. It's like this guy doesn't actually connect to this one. It's like 4 of these 4-bit Carnot maps stacked one on top of the other. So it's actually a 3-dimensional structure. It's a 3D Carnot map rather than a 2D Carnot map. So you have to remember that. But then if I try to store 2 patterns, you get this really crazy behavior. That both patterns they're orthogonal. The 2 patterns are actually stationary. But then you get a bunch of other patterns which are also stationary. So if you look at the blue strips, if you're in the middle of the light blue strip, and if you set the network at that location, it's not going to change because there is no bit flip that's actually going to lower the energy. If you set it in the middle of the dark blue region, it's not going to change, right? So although you have all of these other regions which are nice memories, for most of this energy surface, you have all of these fake memories which didn't really happen. Interestingly enough, that's how we too operate. We have a lot of fake memories, believe it or not, right? So what we get is we get perfectly stationary and stable memories, but we get a lot of fake memory local minima. But you do have this thing that every real memory has a local bowl, and if you start off in that bowl, you're going to actually go to that memory, right? Now, if I try to store 3 non-orthogonal patterns, now because this is a 6-bit network, I can't have more than 2 orthogonal patterns. When I get to more than 2 patterns, they cannot be orthogonal. So if I try to store 3 non-orthogonal patterns, you get this crazy behavior where all 3 are perfectly stationary and stable, meaning I can start off near these patterns and I can recall them, although I get a lot of spurious fake memories. Now, the point to note is that 3 is much greater than 0.14 times 6, right? It's exactly half of 6. So this 0.14 limit that Hopfield came up with doesn't always hold everywhere. If I go up to 4, then again you get this really interesting behavior where all 4 are perfectly stationary, and interestingly enough, you actually get fewer spurious minima than when you were trying to store only 2 things. So sometimes trying to store more, trying to remember more is better than trying to remember less, which is an odd thing, right? And so on. So you can just keep building this up, right? If I try to store 6, then you get all of these ghosts. Every pattern's negation is also a valid memory, right? And you get a lot of interference. But many of these patterns are actually stable. So even though you're trying to store 6 patterns in a 6-bit network, you're able to store up to 4 of them quite stably. And I can try to do this with an 8-bit network. You get the same kind of pattern, right? Behavior. If I try to store 2 orthogonal 8-bit patterns, you get some spurious memories. If they are non-orthogonal, so here's the interesting thing. When the memories that I'm trying to store are not maximally distant, you're actually able to do a better job of storing these memories than when they're as far apart as possible from each other, which is kind of weird. When I try to store 4 of them, I can store all 4 if they're orthogonal. But if I try to store 4 non-orthogonal memories, then the behavior that I showed earlier actually doesn't happen. In this case, for non-orthogonal patterns, you get ghosts. And if I try to store 8 of them, there is really no storage, right? Everything gets wiped out if they are orthogonal. So here's what we get. You get many parasitic patterns, undesired patterns that also become stable or attractors. You get, but there's also apparently a capacity to store more than 0.14 n patterns. So where do the parasitic patterns come in from? It turns out that if I'm storing 3 or more patterns, if say YA, YB, and YC are all stationary, then the sum of the 3 patterns is also guaranteed to be stationary. And so that's where you actually get parasitic patterns from, number one, if you're using Hebbian learning, not if you're using any other mechanism to learn these weights, right? And secondly, you also get these other random local energy minima from the weights matrices themselves, which also end up being fake memories, right? So getting back to the point, it seems that we can store more than 0.14 n patterns, but then we need some other strategy. So what we've seen so far is that even simply using Hebbian learning, it's possible to store a fairly large number of patterns. If I have n bits, I can store up to n patterns. For example, when I was trying to store, in the 6-bit network, I found myself able to store six patterns, right? If I have n bits, I can actually store up to n patterns. But what I would like is some non-random way of being able to know which patterns I can store and actually generating networks that can store these patterns. And Hebbian learning provides no guarantees if you go beyond just one pattern. After that, it's sort of kind of random, right? So we also find that patterns that are non-orthogonal are often easier to remember, meaning if patterns have some similarity with each other, for some reason it becomes easier to remember those than if they are maximally dissimilar. And so the question is, can we actually come up with some mechanism for designing these weights matrices, which is not based only on Hebbian learning, which will allow me to store a larger number of patterns in a more controlled manner, number one. And number two, for an n-bit network, can I actually store more than n patterns, right? If I'm trying to store if I'm trying to store n-bit patterns, can I store more than n-bit patterns? After all, we know that you can have up to 2 raised to n possible n-bit patterns, right? Ideally, I would like to be able to store them all based on content, but of course that doesn't make sense because that means that every memory is a valid memory, right? But nevertheless, I'd like to be able to store more than n of these guys. So can we actually do this? And this is what we're going to see in the next class. So the story so far, just adding on to everything else, the network must be designed to store the desired memories. The memory patterns must be both stationary and stable on the energy contour. This can be trained using Hebbian learning, but and Hebbian learning guarantees that a network of n bits can be trained to store up to 0.14 n patterns with less than 0.4% probability of error. However, empirically, it seems that we can actually store much more than 0.14 n patterns. So we're going to investigate these two claims in the next class, that you can always store up to n orthogonal patterns such that they're stationary. And I'll let you figure out why before the next class. And that I can avoid spurious memories by actually adding some noise during recall. So I'll stop here. Questions? Yes?
So Hopfield is a person? It's not named after the network?
No, John Hopfield is a person. He's a very famous person.
I thought it's named after a network.
Why would you name a person after a network?
I mean, like, it's like, yeah, you have a few, but then you, like, hop around.
No, John Hopfield was a person. And in fact, everything that you know about Jeff Hinton's work actually builds on Hopfield's work, as we will see in the next couple of classes. Thank you. Yes.
So you said every pattern is going to be stored in one minimum, yeah?